things. Dear Father, we thank you for this day again, Lord. Thank you for these students and their patience. Help us to make the most of the time we have left today. In your name I pray. Amen. All right. So, yeah, I'm definitely working on owing you several video lectures as we go on here. It seems like I'm working myself into a deficit of class time this semester. It's unfortunate, but anyway, so we're continuing through section 6.1, which is on modules, right? And section 6.1 of Rotman, I will probably transition to Dummett and Foote sometime soon. This is the second edition of his advanced modern algebra, which is, I don't know if you've noticed or not, really a lot of fun to read. I was contrasting the prose in this to Dummett and Foote, and I don't know, there's really no contest. I mean, I think Dummett and Foote is just a little bit more packed, actually. Maybe, well, anyway, I do like this book. Edan, yeah, that's not a word. Ooh, I like that. That's like if my son was a Pokemon and he went to the next level, he wouldn't be Dan anymore.
I think that's called advanced modern English.
Let's go with what I can do today. There we go. Problem solved. So, excuse me. I am still recovering from breakfast. I inhaled a piece of something as I was eating, because I was eating on the road, literally. 1-6. Is that against the law yet? Let's see here. We've done everything else, but it seems like we should have started with eating. Maybe we should. That's true. You know what? Maybe you're right. Maybe we're at the cusp of history. Like, we've reached this place where we can't do anything in our car except for, like, drive. But yeah. I mean, every once in a while the car's going to kill you. But setting that aside, I guess it's better than killing yourself. Let's see here. If R is a ring, with the car. All right. If R is a ring and we have a left module M, and that left module is the ring itself, all right, then, all right, the endomorphisms of the ring to itself are isomorphic to the opposite algebra. Well, the opposite ring, rather. And this is an isomorphism of rings. All right, so let's go through it again. So we define phi going from maps from R to R via phi of f equal to f of 1, right? So notice that 1 phi of f plus g is equal to f plus g of 1, which is equal to f of 1 plus g of 1, which is equal to phi of f plus phi of g. Also, notice that if we look at left multiplication by r of x be definition Rx, then if you calculate phi of LR, all right, then that's equal to what? LR of 1, which is R. Thus, phi is onto R, right? Now, I got hung up here when I was going through the proof again for myself by fussing about whether or not L sub R was actually in end RR. But the reason I shouldn't fuss about that here is that I'm really only interested at this point in the proof if phi is an isomorphism of abelian groups. So as an abelian group, these are still in there, even though if you fuss with, well, anyway, I'll just stop there. 3. Still maybe not make the. I guess phi is, if we have phi of f equal to phi of g, what's that say? That says that f of 1 is equal to g of 1, right? But the 1 generates the ring, and that implies that f is equal to g, right? So if two functions are equal on a generating set, then that implies the equality of the functions on the ring, right? Well, ring 1 is a ring with unity, so. I mean, what does this mean?
Yeah, does that mean?
I think, or I forget if it's on the left or on the right, but either way, we win.
It just means you take anything.
Yeah. So all ring multiples of 1 is the ring.
So if R were a field, for instance, then you could pick any non-zero element to work with.
That's also true, yeah. Okay, anyway, this is the uninteresting part that he doesn't even write down, right? That we were getting stuck on, because this proves that it's an additive bijection. Additive bijection from here to here, that's all we needed. We were trying to prove more last time, which is what is confusing us, all right? Now it's time for the more, all right? Here's the more, because we have not yet all I've done so far is to prove that these two sets have the same size and their one-to-one correspondence by this map. Now we'll prove that this map transports the appropriate algebra structure that's claimed, not that we were half understanding last time. Okay, so.
Okay, so 2 give that it's the same size, and then 1 shows that it's additive.
Yeah, in other words, it's a homomorphism of these abelian groups. Yeah. Okay, so at this point, continuing, if we look at phi of fg, right? And so now we're going to let f be a mapping from R to R in and R, okay? And also G, so let G and F be endomorphisms of R to R. Look at phi of fg. Phi of fg is f composed with g acting on 1, which, by the way, is f of g of 1, which, by the way, is f of g of 1 times 1, because it's a ring. You can always multiply by 1, right? But then f is an R map, which means we can pull R scalars out. Right? So that means we've got g of 1 times f of 1, right? And then that is what? Well, that is phi of g, right? Times phi of f.
So you said this because F is an R map.
Yeah. Well, this step right here. But in other words, this, of course, is the opposite multiplication acting on what? Phi of f comma phi of g, right? It's the opposite multiplication on fg, right? And then he says well, he doesn't say this, but I'm saying it. Let psi be a mapping from the ring to the opposite ring, right? That be defined by psi of AB equal to, BA. So the anti-isomorphism, right? Then, if we look at psi composed with phi, that will be a mapping from endomorphisms of R to R. Phi takes us over here to R again, and then psi takes us to R up, so to speak. But anyway, I spent entirely too long on this already. So let me just finish this thing already. So what's psi composed with phi? Psi composed with phi of fg is what? It's psi of the opposite multiplication of phi f. Well, let me just forget about the mu op. Let's just write down. We have phi of g, phi of f, right? But what is the opposite? This is the anti-isomorphism, so it switches the order. And there you have it. Oh, I'm sorry. That is not the map I want. Oh, dang it. Now I'm confused again. This stupid opposite thing. Twist it all up. Let's see. So to find the isomorphism from the endomorphisms to the opposite ring, I need an additive bijection, which is also doing what? Sending 1 to 1. That's fine, right? Isomorphism of rings, we also need to have what? We also need to have phi of the multiplication, right? Of, let's say, f and g in endomorphisms. That's supposed to map to the corresponding multiplication, which in this case is the opposite multiplication, right? Of what? Yeah, phi of f and phi of g. Look, I already have that. Let me forget this. This last step is, this last line, I think, is destructive to my larger goals. It made sense to me last night, but it's no longer making sense to me. So, let's apply Occam's razor to my proof. Yes. What's that? Yeah, the best razor. So that's the true competition for, what is it? Is it Gillette or Gillette? I don't know. All right, anyway, so there you go. We good? Now, the next thing, is he notices, and this is kind of a nice comment, if we have A maps to A transpose, then you notice that AB maps to what under transposition? AB transpose, which is B transpose A transpose, but hold on a second, only for what? AB in, he says mat n K, where what? K is field, right? A commutative ring. Well, I don't have to say field, that's too strong. Commutative ring will do, all right. So in other words, the transposition map is an anti-isomorphism if we're working with matrices over a commutative ring. However, if you just look at the 2x2 matrix multiplication and check the Sock-Shoes rule for a matrix full of things not necessarily from a commutative ring, it's easy to prove just by explicit multiplication of the 2x2 matrices that there's no reason that AB transpose should be equal to B transpose A transpose when the matrix is filled with things that don't commute. If you look at proving the proof of the Sock-Shoes rule, there's a step in the proof where we use the fact that the entries of the ring commute. So the fact that we're working with a commuted ring is a necessary truth in order to get Sock-Shoes, in which is what's necessary for the transposition map to be an anti-isomorphism. So given that, this proposition is a little bit more impressive because it says, you know what, even for any ring, we still have the following. We have that the n by n matrices over the ring, the opposite algebra of that, op, is isomorphic to the n by n matrices over the opposite ring. Now, this is not assuming that the ring is commutative. All right? So, of course, we can look at, again, the isomorphism actually is going to be transposition. So, the proof is not assuming it's commutative. Use phi to go from mat n r op to mat n r op, you know, phi of A equal to A transpose, okay? So we need some notation, all right? So in here, I'll say that A star big B is BA. And over in here, I'll say that A little star A times B is BA. I'll tell you what, to make this a little bit easier to see, let me just use a five-pointed star, five-pointed star, like that, for the matrix, the opposite matrix multiplication, right? And I'll use an asterisk for the opposite ring multiplication. And anyway, it's clear that phi composed with phi is the identity, right? Well, phi composed with phi is the identity on this set. It's the same set, right? Just different algebra structure. So it is a bijection under the transposition because transposition is its own inverse at the level of sets, right? Now we need to fuss whether this bijection has actually got the right algebra structure, right? In other words, whether it transports the opposite product of matrices to the matrix product over the opposite ring, okay? And I think this proof is worth looking at just because it explores these ideas. The result, actually, I'm not sure. I don't know. I'm not. Again, I think you can appreciate that it's interesting because it's not true for. I mean, anyway, it's kind of surprising given the comment, the necessity for the commutative case. Okay, so anyway, getting to it. So here we go. A star B maps to what under transposition? It maps to A star, five-pointed star, B transpose, right? But what's that equal to? That's equal to BA transpose, right? And when I first did this proof, I then wrote down A transpose, B transpose. And then the proof became like stupidly simple, and I didn't understand what I was doing because I'm an idiot. And you can't just go A transpose, B transpose here. It turns out that it's true, but it's not the Sock-Shoes rule. It's a little bit more, right? I can't go further because I'm not assuming A and B have entries in a commutative ring. We're stuck there at the moment, all right? So on the other hand, we could just look at A transpose, B transpose, the ijth entry, all right? Look at it directly. What would that by definition be? By definition, that would be the sum over K, right, of A transpose ik. And then here, this is an entry in the ring, right? So when we're talking about matrix multiplication and the opposite ring, that means the matrix at the component level, it's done with the opposite multiplication. That's what that means. It means we put a star here. We don't just do ordinary ring multiplication. Okay? And so that's where the magic happens. We don't get to commute the elements, but the definition of the opposite multiplication commutes them for us, right? then definition of, I'll do it down here, definition of transpose gives us A, JK, oh, I'm sorry, B, BJK, AKI, which, by the way, is what? That is B, BA, JI, right? Which then is nothing more than B, A, transpose, IJ. So these two being equal for all components then gives me what I want, which was to write, but it's not sock shoes, right? It's, I'm not sure what the right joke is to make here. Something about putting on your opposite socks and opposite shoes or something, but it's here. So that's A transpose, B transpose by this calculation, right? And that's what we need, right? We've just shown that the opposite multiplication, this is what? This is what? This is, what is this, though? This is phi of A, phi of B, right? I think. Or have I done that wrong? Yeah. So that proves the proposition. All right, let's move on here. Let's not get stuck in opposite world forever. So next up is submodules. What is a submodule? Actually, I should probably just erase this and put it behind us. All right, so what is a submodule? Can you guys tell me? A subset which is also a module with respect to the natural operations? Right, yeah. So if M is left R module, then N a subset of M is submodule of M denoted. And you notice here, he says this, but he doesn't really stick to it in everything he writes. He'd be really fussy here, but, and this is not just him. I mean, some people, when they write subset, if you write like W is a subset of V, they actually mean that to mean W is a subspace of V. So there's not universal agreement about, I mean, for me in linear algebra, I'm kind of dogmatic about subspace I write less than or equal to, right? But that maybe is much like the use of composition in your earlier courses. It kind of fades when you go to higher math. People are not as insistent. They might just use subset to denote subspace. So then you're like, well, what if it's just a subset and not a subspace? Then how would I express it? Well, you use words. Except if you look, every so often he slips back into set theory for a subset of a submodule, subset of a module, which is not actually a submodule. So he does not, even in this, in the next couple pages, I found a use of subset, which is just set theoretic. And clearly so, because it's a finite subset of a vector space, which is clearly not a submodule. Right? Because submodule is going to reduce to subspace in the context of the F module, the field module of a vector space. I mean, this is a generalization of that idea, in my view. Anyway, is an additive subgroup. So I'm just trying to say, beware. It's always good to use words to emphasize what you mean. Additive subgroup, and Oh, I already wrote that. M closed under scalar multiplication. And so what does that mean? That means that if R is in R and N is in N, then what? Then Rn is in N again. And then he has a list of grievances. No, I mean examples. Let's see here. About 10 examples. No, nine examples. What's that? You see, did you make my 9 German? Okay. 9. Wait a minute. No, that's what was that? That's something else. So what are our examples? So first of all, 0 and the module itself are non-proper submodules, right? If you have n, a subset of m, and not equal to m, then we write n. So that's proper submodule. Yeah, 0 is a proper submodule. But if you want it to be not 0, you say a non-trivial proper submodule. A submodule of a ring itself, if you take the ring, if you look at R sub m equal to R, and then left ideals are submodules. A submodule of a Z module is a subgroup, all right? So for Z module, submodules, and just subgroups. What's that? Say again, what?
When you write submodule and submodule, proper submodule of that, previously we would just just leave out the bottom line rather than cross it out.
Oh, I don't know. I'm just telling you what Rotman's doing in this section.
Yeah, I'm just checking.
For us, you could use whatever notation you'd like, but just add some words to make sure I understand what you're saying. If it's, it might be clear from your usage anyway. But then the example I'm most interested, of course, is when we're looking at the vector space as a fx, a left fx module, right? I guess it's this, but we usually call it V upper T, right? Where, you remember, we had T, f of x acting on how'd it go? F of x acting on a vector. We took the polynomial of the given transformation acting on the vector. That was our module multiplication, right? For a given endomorphism, given linear t going from t. Words. T going from v to v linear. So, what's a submodule? It's an additive subspace. So right there, that's going to be additive subspaces. At least have to be what? Certainly they include subspaces in the vector space sense, but they've got more than that, right? You can look at, I think you can have, is it possible to have a set which is closed under vector addition but not scalar multiplication? Sure, like for example, integers are closed under vector addition of real numbers, but if you scalar multiply them by pi, you're in trouble, right? Like pi times integer is not an integer again. So just the start of the definition of submodule, it does not make it a subspace, right? We just some subset which is closed under addition, right? And then we need what? We need this condition. So if W is a subset, subset of V such that what? We need f of x w equal to f of t w for all f of x in the field, the polynomial, and w in your w, big W. So anyway, one of your homework exercises is to prove, and I've almost done it here, that what this means is that the submodule of this, V upper T module, those are the so-called invariant subspaces, right? They're the invariant subspaces of the linear transformation. I've almost done everything you need to do, but you can prove, I'll just put some dot, 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 you can prove that we have to have this T of W is in fact a subset, set theoretic subset. See, I don't like this. I'm sorry, I can't adhere to that notation. I'm going to have to say, I want a subset to be subset, otherwise I just go nuts. But anyway, so we need this condition that T of W is a subset of W. In other words, that W is a T invariant subspace of V. Right, so that's the submodule there. One of your homework exercises, when I finally write them up, will be to finish that. I've almost done it. Look at f of x equal to x, right? It holds for all polynomials. It certainly holds for the ones most interesting. Okay. Other examples. He defines what we mean for he starts talking about how to generate things. 5, he defines RM. Oh, we did this. We did this. It just recurs to me. We ran into this. Maybe you'll remember this, guys. If R is in the center of the ring, right, then we can define RM equal to what? Rm, such that M is an M. So all R multiples of M, but that only makes sense as a submodule if R is in the center of the ring. I was commenting to you guys last semester that there's a little bit more non-commutative ring theory stuff in the book we use this year. In the past, I've only given the generator of something in a ring, typically in the commutative context, in some previous books I've used. So this is kind of interesting non-commutative extension of that idea. But on the other hand, he defines for something that's not necessarily in the center, you can let J equal to RR, which is the left ideal generated by R. That is a left ideal generated by R. And then he defines Jm to be AM such that A is in J and M is in M. This is, again, a submodule. Or then he's like, more generally, if you have any left ideal J, you can define Jm to be the sum over J sub I, M sub I, such that Ji is in J and Mi is in M. Six, intersections. In other words, the intersection of submodules is once more a submodule. All right. 7, we can define S plus T in the usual way. S plus T such that S is in S and T is in T. That defines a submodule. Right? And in fact, this is generated. So this submodule contains both S and T. right? So this submodule S plus T contains the S submodule, and it contains the T submodule, and in fact, you can prove that it's generated by their union. So this angle bracket means generated. In fact, that brings us to, oh, that was 6. Wait a minute. No, 6, 7, oh. Dang it. What have I done? Oh, I can't count. That was 8. Which explains why I've suddenly used a notation I have not introduced yet. So in 7, we introduced this angle bracket notation. Sorry. So what does angle bracket x mean? It is finite sums of r sub I, x sub I, such that Ri is in the ring and x sub I is in X. So this is a left module generated by X. All right. We say that a left R module is finitely generated if it has a what? A finite generating set. Very good. And in the case that the generating set is a singleton, we allow ourselves a slight abuse of notation, right? If X is just the set containing X, then our notation is that this is actually just that. All right. And that is also, this has a name. This is the cyclic submodule generated by X. All right. So we learned in Math 321 that if the dimension of the vector space is less than infinity, then V, if and only if, in fact, V is finitely generated, translating it back into our dimension language. And then his 9th example concerns the Galois group and the fact that the Galois group is a left KG module. And he says, we say E over K has a normal basis if and only if E is cyclic. I mean, we're cyclic with left, it was a cyclic left KG module. KG is the group algebra. So KG would be, for us a lot of times, would be like Q times G. It's a set of all formal rational linear combinations of the finite group, which becomes an algebra. I haven't defined algebra in here yet, but I will. So the first section on modules in Dumb and Foote defines algebra. There's a couple of pieces missing here and there in the first section of Dumb and Foote that we haven't quite got to yet, which we will. So what's passed here in this section? So next he defines kernel, he defines image, and he mentions that those are submodules. The kernel, so if we have so I'm just going to give you a rundown of the next couple pages here, and we'll stop for today. So if we have F going from N to N, M to N in our map, and these are left R modules, all right, then kernel of F is a submodule of M. The image of F is a submodule of N. All right. If you have a generating set, he has the proof that if we have a generating set for M, and we can prove two functions are equal on a generating set, then they're equal on the whole left R module, right? So the generating set thing that I used earlier today for the purpose of proving that the mapping was onto in the opposite thing we did to start, that generalizes here as well. All right, if we have equality on generating set, we have equality of R maps everywhere. You can define a quotient module. What's the quotient? If you have N as a submodule of N, you can define M over N. And it's the same as usual. It's M plus N, such that M is an M, right? So this is the quotient module. And the usual song and dance works there too. When are two cosets equal? They're equal if the difference of their representatives is in the quotienting submodule. It's in N. Now here's a new one. Definition for F going from M to N again. It's cokernel, that's a new one, right, is coker F, is the n mod the image of F. That's something we can do, right? If F is a submodule of the image of F is a submodule of n, the codomain, then that quotient makes sense. What does that quotient define? What is that? What does that coset space just describe for you? It's got stuff outside of where we can get to. Stuff outside of range F, right? So F is surjection if and only if what? Right, if the cokernel, coker F, is 0. See, because if the cokernel of F is 0, that means that the image of F is equal to n. And so you see why it's called the cokernel. Because it's, well, anyway, that's kind of neat. Now we have something that just in the same sense that, kernel being 0 gives you injectivity, cokernel being 0 gives us surjectivity. Yeah, why didn't we talk about this in linear algebra is a mighty fine question. And I think the answer goes back to student evaluations, ultimately. Because that's where, if linear algebra every year encouraged me to be better at linear algebra and to think deeper about it for the next generation, I like to think I would be at a cokernel by now. But every year they beat me back, beat me down, and talk me out of doing the next thing. So I think the short answer to your question, why we don't do that in linear algebra, is course evaluations. Maybe if I didn't have a family to feed, I'd be different. I don't know, but you should only teach math if you have like a monk-like existence. You don't have to care about your something like that. No, I don't know. I guess it's just a little bit too abstract. I mean, more honest answer is just kind of out there.
Yeah, we didn't get to quotients until like the very end.
Now I have fixed that a little bit. Like we did, I have quotients on the second test. So we've already done quotients and duals at the 60% mark in the course. So the last 30%, I'll be trying to bathe eigenvectors and the other constructions in the light of dual spaces and quotient spaces in as much as possible. That's an improvement I saw that I could make this year, so I am. Okay, so what's passed here in Rotman is then first isomorphism theorem, second isomorphism theorem, third isomorphism theorem, the correspondence theorem, which I sometimes call the lattice isomorphism theorem. That's that inclusion reversing deal that concerns not just one subspace, but the network of subspaces for a vector space, or the network of submodules for a submodule, and the way they're related. And the proof of those is basically, hey, we proved it in group theory. So it's still an additive abelian group, so you get the basic set theory from that. And then what's left is to prove that the necessary constructions are R maps, which is a straightforward calculation. So I'm just going to push past that. So next time, I will try to start talking to you about how we can understand surjectivity and injectivity in terms of diagrams. These diagrams that he talks about at the end of the section. He talks about short exact sequence and these sorts of ideas, which is the starting of what I would call homological algebra, which is the bedrock on which algebraic topology is laid. So, yeah. Anyway, I shut up. Thanks, guys.